Okay, this is Chapter 2, Motion Along a Straight Line. Now, in this chapter, we're going to talk about some physical variables and the relationship between them. We're going to talk about straight line motion, and we're going to talk about it in terms of the physical variables position, velocity, and acceleration. Now, velocity and acceleration are going to have two flavors that we're going to discuss, average and instantaneous. And we're going to graphically look at all these three parameters, position, velocity, and acceleration, and be able to interpret them and the relationship to each other. There's also a lab on this. Objects that are in straight line motion with constant acceleration, we're going to talk about how the position and velocity changes for constant acceleration. And we're going to look at a special case of this, freely falling bodies. That's when the acceleration is due to gravity, which is a constant acceleration. Lastly, we're going to take a very quick look at straight line motion when the acceleration is not a constant, but that's not a huge priority in this chapter. Now, kinematics is the study of motion. And when I say motion, I mean we're going to talk about position, velocity, and acceleration. They're the important physical quantities that we're going to talk about. So if you think about a bungee jumper that's moving up and down, this bungee jumper is going to jump off the bridge and it's going to start to fall faster and faster and faster. He's moving. We're studying kinematics because we're talking about his velocity, we're talking about his acceleration, and we're talking about his position. And as he reaches the end of his rope, then he's going to start to slow to a halt and then move back upwards. So we're going to be able to talk about his position, velocity, and acceleration throughout this entire process. So let's just get right started here, and we're going to first talk about displacement. You can also think of this as distance. However, keep in mind that distance is how far you traveled, and again, displacement has some directional information involved with it. So if you are drag racing with your buddies on Route 11, you might start at some initial position, and you might finish at some final position. I'm going to call this X1 and X2. Now, if you know how far this is, I'm going to say that this was maybe 100 meters, and I'm going to say that your starting position was 0. Now, I'm doing this a little bit differently than figure 2.1. I'm making the numbers just a little bit easier to understand. You can say that you know that the displacement being the change in position, that's what that Greek symbol delta means. The change in position is equal to x2 minus x1, which would be 100 meters minus 0. So your change in position is going to be 100 meters relative to where you started from. Now, as you covered this distance, it took you a certain amount of time to do that. And we're going to say you started the clock, time is equal to 0, as you pass the starting line, and suppose it took you 10 seconds to do so. We can describe your average position over the interval as the change in position divided by the change in time. So we could write your average velocity is equal to x2 minus x1, and similarly t2 minus t1, or 100 minus 0 divided by 10 minus 0. This has units of meters, this has units of seconds, so we're left with 10 meters per second. Now the book gives an example of initial time and initial position not being equal to 0 if you'd prefer to see a slightly more complicated version of this. Now, the change in position and the velocity, they're both positive. What that means is we've defined positive to be in this direction from left to right. This is the positive x direction. Similarly, we typically tend to define the positive y direction to be upwards. Now we can consider negative velocity. Now, negative velocity, if we consider a truck moving in the opposite direction, and I'm going to keep the nomenclature the same, where it took the truck 10 seconds to go from the right to the left, starting with a time equal to 0, and having an initial position now of 100 meters. Remember, the 100 meters is relative from the starting point in the last example. Now I would talk about a velocity that is change in position divided by the change in time, and now it's going to be 0 minus 100 meters divided by 10 seconds minus 0. The velocity is now equal to negative 10 meters per second. All that really means is that the truck is traveling not in the positive x direction, but in the negative x direction. Now, we can look at this graphically. We can look at a position versus time graph, where here I've drawn the position, or here I've written the position along the y-axis and the time along the x-axis. Now, we do that because time is the independent variable, and we're measuring position against it. Position is the dependent variable. And if I draw the truck's position as a function of time, then I can look at what the velocity really means. We know that the velocity is equal to the change in position divided by the change in time, or x2 minus x1 divided by t2 minus t1. And if I pick this to be x1 t1, and if I pick over here to be x2 t2, then I know that this right here is my change in x, or x2 minus x1, and this guy right here is my change in time, or t2 minus t1. So what this is also saying is, if you think back to your days of algebra, we know that the slope of a line is going to be the rise over the run, or typically the change in y divided by the change in x. But in this case right here, along the y-axis I actually have my x, and along the x-axis I have my time. So this is also the change in position divided by the change in time. So the slope of the position versus time graph is also the velocity, the average velocity. Now, the instantaneous velocity is a little bit different. So if I draw my curve as from the last guy, and if I consider my average velocity over a long time interval, then that guy would be described by this triangle. Change in position divided by the change in time, and along here I would get my average velocity. Now, the instantaneous velocity is actually taking the limit as as delta t approaches 0 of change in position divided by the change in time. So you can think of, rather than looking at big long time intervals, maybe I'm looking at a time interval like that. Or maybe I'm even looking at a very, very, very small time interval, one described by that line. Change in time over change in x. So the instantaneous velocity is also known as the derivative of the position versus time. Now we need to know that the average speed is not the magnitude of the average velocity. Now we can learn a lot about looking at a position versus time graph about what's going on with the average velocity. So if I were to draw a graph where I put time on the independent axis and position on the dependent axis, then I can draw the position of a car, for example, as a function of time. Now, if I want to ask myself what is the average velocity of this car as a function of time, well, I know how to do that. I look at the change in x divided by the change in time, or x2 minus x1 divided by time 2 minus time 1. And so over here I would have x1 time 1, and over here I would have x2 time 2. And if I were to say draw a line from here to here, then this would be my change in time, or my time 2 minus time 1. And then this right here would be my change in x, or my x2 minus x1. So my average velocity would be this vector that I drew right here. Now we also know, remembering back to our algebra days, that the slope was equal to the rise over the run, and typically you would write that as delta y divided by delta x, but because x now is on the y-axis, it would be change in x divided by change in time, where time's on the bottom axis now. So the slope of our position versus time chart is our velocity, and in this case it's our average velocity. Now I made the designation between average velocity and instantaneous velocity because if we look at, say, our velocity over time, and suppose you're at a stoplight, your initial velocity is equal to 0, and then you punch the gas and you get her up to 40 kilometers per hour, and you drive to the grocery store, slow down, pull into the grocery store, your instantaneous velocity, or your velocity at any given time interval, is going to be different. Now, if you ask yourself what the average velocity for the trip is, well, then you would take your change in position, how long you had to drive to the grocery store, divided by your change in time, and you'd get your average velocity. But as you can see here, if I look at small time intervals at any given time, my instantaneous velocity is not necessarily equal to my average velocity. We write the instantaneous velocity by looking first at the average velocity, which is the change in position divided by the change in time, and looking at that as the change in time approaches 0. So we would even, in the language of calculus, we would say that the instantaneous velocity is the derivative of position with respect to time. Now, also here, I need to note that the average speed is not the magnitude of the average velocity. And a good example of that is if you were, running around your college track, you would say that after I've gone around the track once, that my position, my displacement, is actually equal to 0, because I have ended up where I have started off. However, the distance that I traveled was once around the track, probably a quarter of a mile. The average speed is equal to the distance divided by the time. The average velocity is equal to the change in position divided by the time. So the average velocity would actually work out to be 0. Now this chart shows what a much better version of what I was showing on the earlier plot, where I say, okay, we can go ahead and we can calculate our average velocity. Here I'm showing position as a function of time, and we calculate out our average velocity, our change in position divided by the change in time, simply by looking at the slope, or the change in position divided by the change in time. Now if you consider the limit as delta t starts to approach 0 of the change in position divided by the change in time, so now I've picked a smaller time interval and I take the slope of that, we can actually see that the velocity, which again is the slope of this green line right here, is a little bit different now that I've chosen my time interval to be smaller. And if I choose my time interval to be infinitesimally or extremely small, so the limit as delta t approaches 0, then I'm actually looking at the slope of the tangent line of the position versus time graph.